Today I'm going to be talking about the CYK algorithm. The CYK algorithm is named after the three scientists which created it, which were named Cork, Younger, and Kasmi. This algorithm is basically tells us for a given string whether it belongs to a particular CFG or not. Belonging to that particular grammar would mean that the string is a member of that grammar, and that is why this algorithm is also called this membership algorithm. So, starting off, to understand this algorithm well, it is best to explain along with an example. So, we have an example over here. This is the particular CFG grammar which is given to us. Now, do ensure for this membership to be applied to this grammar, the grammar should be in its CNF form, which is the Chomsky normal form. A grammar to be in its CNF form would mean that a variable would give other two variables on the RHS, or a variable would give a terminal. To ensure that the particular grammar is given in the Chomsky normal form, we need to take care of three rules, which is given by the acronym NEW. I like to use it. NEW meaning there should be no null productions, there should be no unit productions, and there should be no useless productions. As you can see by particular grammar that I have taken conveniently, none of these conditions exist, hence we need to do nothing about them. Now coming back to the algorithm, we're given a particular string we have taken here, which is BBAB. Now what we would like to do is to spread out this string and number them as index values 1, 2, 3, 4, let's say. Now accordingly to these numbers, we will like to make a sort of a half matrix for them over here. The way we'll do that is by making the index numbers like this. Need to ensure that this outermost square that we will make should be 1 comma 1. Now what we can see, ensure that this column should be 1 comma 1, or you can ensure this column should be the other extreme such as 4 comma 4, and this should be 1 comma 1. This means that the index we have done for the matrix is correct. Now we can move on with the algorithm. First of all, so now we'll start filling up this matrix starting from the outermost diagonal, working our way up till the innermost square. So what we will do is, first of all, let's start with the outermost diagonal. The outermost diagonal consists of 4 squares, as you can see, or 4 cells, which is 1, 2, 3, 4. In order to fill up these cells, we will have to look at the index values. So this, as I had previously mentioned, the first cell is 1 comma 1. So 1.1, you would like to convert this into the index values of the strings that we created up here. So as you can see, 1 comma 1 would be this index value. So that would mean the B in this string. So after you got down the cell and you found the index values, you will write down what is in the string at that index. So we will write B. So now we got to look at the grammar and see what is deriving B, or how can we get this B. So according to the grammar, we can see that the variable B of the production B gives rise to AB, gives us B gives rise to AB slash B gives us the symbol that we need, which is this one. So hence we can say that this small b, which is a terminal, is derived from the production of capital B. So hence, like that, we can fill the position of the cell 1 comma 1 with the variable B. Once that variable is filled, we can just write it over here. Similarly, we'll do for all the other cells and find out which variables are fitting into these cells. To do that, we write the rest of the cells that we need to figure out for. So this cell will be 2 comma 2, and this cell would be 3 comma 3, and the last cell would be 4 comma 4. Next, we write whatever comes according to the index, and according to the string given to us, we write the symbol which is coming at that particular indexes. So 2 comma 2 would basically mean the second B over here. So this will write over here. 3 comma 3 would mean this A over here, which is A, and 4 comma 4 would mean this last B at the end of the string. Once we are done, then it's just a matter of fact that what symbols or what production rules derive these symbols. A is derived by capital A production, and B again is derived by the capital B production. So these are our values. So we just have to fill this in now. 2 comma 2 is a capital B, 3 comma 3 is a capital A, and 4 comma 4 will be capital B again. So like that, we have filled our outermost diagonal. Now we move to the inner diagonal right besides it. Next, the inner diagonal, we have got 3 cells we need to deal with. Namely, I like to read my indexes from here and then the top one. That makes it convenient as the smaller number will generally come before that. So we are getting this indexing values. So 1 comma or 1 comma 2 can be viewed as, if you were to break it down further into its previous indexes or the previous diagonal values, you can break it down something like 1 comma 1 concatenated by 2 comma 2. So basically, we need to see what are these cells, take that symbol, concatenate them, and we will get the symbol which should be in this cell, which is 1 comma 2. So 1 comma 1, as you previously saw, we can even refer the diagonal we filled earlier. 1 comma 1 is filled by a capital B, and the cell 2 comma 2 is also filled by a capital B. So B concatenated at B will give us BB, and then we can look at our productions and see what derives BB. So as you can see, the only production rule which derives BB is this one, the production rule for A. So we can see that BB is derived by capital A production. So we can say that 1 comma 2 should be filled by a capital A over here in the matrix. Similarly, we can fill in we can find out the symbols needed for the other cells. So 2.2, as you can see from our diagonal, is a capital B, and 3.3 is a capital A. Now, unfortunately for our case, B dot A I do not believe is part of our grammar. So we can just simply write epsilon or phi to indicate that it is, well, it's not, there's no production rule for it. So hence there is no symbol for it, this one. And then for 3.4, 3.3 cell value is a capital A concatenated by 4.4 value is a capital B. Now AB is derived by two of the production rules, which is S and B. So we can write it as S comma B. This comma is gonna be important later. So make sure you write it. So S comma B, and in the cell which did not get anything, unfortunately, we can write phi, which consists of just two cells, which would be 1 comma 3 over here. This should be better way. X and 2 comma 4 over here. 1 comma 3. Let's think about this. 1 comma 3. Now, if you look at the indexing values, now you need to be a little careful at this point. 1 comma 3 actually consists of three numbers, which is 1 comma 2 comma 3, which can consist of these index values. So you got to be a little smart about it. You need a way to divide these equally, and we get it. The 2 is we can divide 1 comma 3 is 1 comma 1 concatenated by 2 comma 3, or you can say 1 comma 2 concatenated by 3 comma 3. And in the end, whatever we fill into these cells can be taken as a union to be filled into whatever we need to fill in the cell 1 comma 3. So from our previous diagonal, we can figure out previous diagonals, we can figure out 1 comma 1 would be a capital B concatenated by 2 comma 3. 2 comma 3 holds phi, which gives us a B, and unfortunately none of the production rules give us a B. So none of the symbols will derive a B, so we can fill this as another phi. Okay, for the next thing we can see it's 1 comma 2, which is 1 comma 2 is a capital A concatenated by 3 comma 3, which is a capital A again, which means this again is not derived by any of the production rules, so we can simply say it is a phi. So as we can see, both of the production rules are 5. If we take a union of these two, this is what we are supposed to fill. The union of the both productions will give us a phi, and that is supposed to be the value for what we need to fill in 1.3, 1 comma 3. So that will be a phi over there too, unfortunately. Next, we'll look at our second cell, which is a 2 comma 4, I believe. 2 comma 4, yep. This 2 comma 4, again, this can be looked at by two of the ways, which is 2 comma 2 and 3 comma 4, and also in the way of 2 comma 3 and 4 comma 4. 2 comma 2 as we see from the diagonal, is capital B, and 3 comma 4 is S comma B. Now you see why the okay. Now we'll see why the comma was important, because B concatenated with S comma B will give us an B dot S and also give us a B dot B. So keep that in mind. And as you see, B dot S is derived by nothing, because obviously it's BS. Uh, Never mind. And B dot B will be derived by capital A production, if I'm not wrong. And yes, it is derived by capital A. Take a union of the both, you will get a capital A. That needs to be filled in 2 comma 4. Wait a minute. Aha. There's also another way this can be done. Oh, just remind. See, almost made a mistake. Don't do this, kids. 2 comma 3 and 4 comma 4, because you see, because 2 comma 4 can be written like 2 comma 2 dot 3 concatenated by 4 dot 4. So 2 dot 3 can be, if you look at the matrix, is a epsilon, and that dotted by 4 dot 4 is B, which just gives us just a B, which is derived by again nothing. So okay, I guess it didn't matter. Now if you take the union of both of these production, that is supposed to be filled in 2 dot 4, the union will be equal to 8 dot 5, which will be equal to A. So we can just fill in A over there. Okay, coming to the final part, now we are at the final square. Okay, part 4 would consist of filling in the innermost square, or final square as I like to call it. Final square is a cell which is 1 comma 4. 1 comma 4 would consist of the numbers 1 comma 2 comma 3 comma 4. That would mean we will get at least 3 cells. Three ways we can find out the value for this. That would include the first one. Let us take it. The first one would include 1 comma 1, or 1 dot 1 times 2 dot 4. The second one would include 1 dot 2, then 3 dot 4. The third one would include 1 dot 3 and 4 dot 4. Okay, so kids, let us work on the first cues that we have. First production is 1 comma 1. So if we see what is 1 comma 1, it's a capital B. That is right. Concatenate by 2 comma 4. 2 comma 4 is an A. We get B dot A, which unfortunately is not derived by any other one. So this gives us a big epsilon. Big deal for that. That's unfortunate. But moving on to the next production that we have. So now let us take the second production that we got here. 1.2 would give us a capital A, and then concatenated by 3.4, which is an S comma B. Again, the comma is important because it helps in getting correct concatenation. This will give us two values, A dot S. Unfortunately, not part of any production. A dot B, it's part of two productions, I presume S and B. A and B, yes sir. S and comma B. Now we take the union of that for this particular cell, that will give us an S comma B. And the final production gives us and 1.3. 1.3 is epsilon, unfortunately, and 4 comma 4 is a capital B. 4 comma 4 is a capital B. Concatenate both of them, you will get a capital B. Unfortunately, none of the production rules derive this. This also results in an epsilon. Take the complete union of all of these cells, you will get S comma B. You take the complete union of all of these productions, you will end up with S comma B, which needs to be filled into our column, which is 1 comma 4, S comma B. Now, the final conclusion which we draw from from this matrix that we have got is that, because in the final innermost square we can see there is an S comma B. If in the final innermost square there is the production or the symbol S, which is the starting symbol, that means that this particular string that we have taken is a part or a member of the given CFG grammar that we have taken. And hence, by working out this matrix and filling out the matrix, we can conclude that the particular string is a member of the given CFG. And that is all the CYK algorithm talks about. Thank you.